from the University of Buenos Aires. First, I want to thank Klaus for the organization, for giving me the opportunity to talk here. And I want to talk about the quantum to classical transition in the word distribution for chaotic system. Probably for all of you, this title doesn't you don't look familiar because many of the talks was about condensed matter of nuclear physics. But what I want to tell you is when I saw the poster in my university of the conference, I say, oh, one of my subjects that I am working completely fits with the conference. In fact, I'm going to show you that I can change the title of my talk. And I can say that my talk is Finite System in Non-Equilibrium from Quantum Quench to Time-Dependent Process. This is the idea of my talk, to show that this title fits. So essentially, I want to explain, I want to discuss the notion of work in quantum mechanics. This is the idea. And to do this, first, let's start with a very simple process, okay? I have a quantum system, okay? This system can be a one particle, many particle, a Bose-Einstein condensate, whatever. It's a quantum system, and this system has a parameter, okay? This parameter can be an electric field, magnetic field, I can change the border or whatever, okay? It's like a piston, a quantum piston, okay, that we learn in thermodynamics, okay? So let's put a thermal reservoir in contact with my system because I want that this process, that my system start in a thermal state, okay? Then I cut the connection between my system and the thermal, okay? And my system, then this is my time equal to 0, and my parameter is at one value, and then I start to move, okay? This parameter, then start the process, okay? In principle, I measure the energy. At time 0, I measure the energy, and I obtain this value, Eg, okay, at time 0. Then I start to change my parameter, then I start to change my electric field, magnetic field, or whatever. And at a final time, I measure again the energy of the system, okay? And I ask you, what is the work done on the system? Probably you think, I don't know, 1 minute, and I say, okay, the energy, you think about the first law of thermodynamics, and I say, okay, the work is the final energy that I measure minus the energy that I measure in the first measure, okay? Well, because we have a time-dependent Hamiltonian, essentially, and we have 2 measurement processes. Okay. And okay, so this is the name of these processes in the literature is the 2 measurement processes. Is that people say that this is the way that is the good way to describe the work in quantum mechanics, okay? But there are a lot of discussion about the work, and essentially, it's very simple to show that work, it's not possible to define an Hermitian operator. It's simple because we have more than, if the Hilbert space is n, we don't have any n values of this quantity, okay? It's very simple to show this. We can see that it's a random variable in this case because we have 2 measurements. Okay, so I'm going to explain that there is a random variable, and you can find many many papers that say the definition of work is rather subtle in quantum mechanics. Okay? And of course, we can define in these processes, it's very simple to define the probability of work. Okay? This was defined in 2 papers like 20 years ago or a little bit less. I say that the work is a stochastic quantity, and this is the distribution, and we have this P are 2 probabilities, okay? One of these probability came from the initial state, because you have the thermal state, and you measure the energy, so you have the probability to measure this state, sorry. Ag is this one, it's very simple. And due to the quantum evolution, you have the conditional probability to obtain the final energy at the final measure, given that the initial state was this one. Okay? Sorry, do you have a pointer? Because my pointer doesn't work. Okay. So, this is the probability of work, okay? And, okay, but the people discuss, is a good definition, okay, thank you. No, but I only want to use the pointer. No problem. But doesn't work also. Oh, okay, no problem. So, the point is this a good definition of work? Okay, in this, people show that the main point that this probability of work fix, okay, this probability of work fix with this identity that probably of all of you know. I did like 10 years ago a course of new trends in statistical mechanics. And the teacher said the most important result in statistical mechanics of the last 50 years was the Wisniacki identity. I don't have time to explain, but in this side you have a value of non-equilibrium. Okay, you repeat the process and you obtain the average of this quantity, and this is equal. This is an equality of an equilibrium quantity, okay? This is the free energy. So this quantity, this identity relates non-equilibrium with equilibrium. And it's very straightforward to obtain the second law of thermodynamics, starting with this, okay? This is very famous, and it was shown in many ways, okay? This is the first paper of Wisniacki in 1997, and okay, but there are many papers theoretical when they show that this identity it's right, and there are many experiments. This is the first experiment that this was done in a molecule of RNI. Of the group of Carlos Bustamante, and there are many. This is classical. There is many papers. This is an oscillator. This is a Wisniacki inequality in an experiment in an oscillator, a mechanical oscillator. This is in an electric another experiment. This is another experiment. This is other experiment. In NMR, and this is the first experiment in a quantum system. Okay, in this experiment, is the first one when they did the 2 measurement processes. Okay. Okay, but if you see this recent paper of Wisniacki, he said, while these 2 measurement definition of quantum work can be justified heuristically by appeal to the first law of thermodynamics. This is what I done. its relation to the classical definition of work has not been carefully examined. The question is, okay, we have the work in classical mechanics, we have this definition, and I say, let's see what happened. What is the bridge between these two? Okay? And he said, okay, we have these both quantities, the probability of work classical and quantum, and he said, one possibility to see if this definition of quantum work is okay is to develop a semiclassical theory and to see if this is the bridge between these two distributions. In fact, he did. In this paper that I show in this PRX, he did. But he did a very simple semiclassical theory in a very simple system that is a one-dimensional. This is the system. This is not general what they did. They take this system. This is a one-dimension quartic oscillator, one dimension, in which this parameter lambda, they move in time, linearly in time, okay? And they develop a semiclassical theory and say, okay, this works, okay, this works very nice, okay. But a semiclassical theory of an integrable system for one dimension is very simple. And at the end of the paper, they say, okay, but the point is, it is possible to develop. What did they do? Essentially, you remember that the probability of work has two probabilities in the definition, in the sum. Okay? Each of these probability, he wrote a semiclassical expression of this. Okay? This express, I'm going to show you in a minute, express this quantity only using classical orbits. Okay? This is essentially. And the red curve is the quantum. This is the semiclassical, and the black one is the quantum result. Okay, and it fits very nice. So, okay, so at the end of this paper, they finish, say, okay, we know that this system is very simple. The question is, it is possible to make the same scheme in a chaotic system? And I say, of course, this is very, very difficult because all the semiclassical theories in chaotic system, the number of the orbit grows exponentially. So, and they say, this is really very difficult. Well, I'm going to show you that this is not the case. I will use three very simple, that people all know in quantum chaos community, these three objects, and I make a semiclassical theory of the probability of work, and I show you that this works very nice. This is the idea of my talk, okay? What are the things that I put together? First thing, Quench, okay? This is the title of the conference. I will use a Quench, okay? But then I will show that this I don't need. But first, let's start that my process is a Quench, okay? Then I will use the phasing representation. This is a semiclassical theory. I will explain what is this. That works very nice. And the third one is that what the people know, Berry-Boros conjecture. That essentially the idea is that the eigenfunction of a chaotic system fill all the energy, okay, all the energy that they are not structured, okay, for example, the Wigner function. Essentially is constant. Okay, this people of quantum chaos know this thing for many years. Okay, let's start. What is a quantum quench? You know, quantum quench. You have my parameter, my electric field, my magnetic field, and I change very rapidly. For some people say sudden quench or whatever. Okay, this is the first point. Okay, but let me explain what is important in quantum quench. It's better to work, not the probability of work, it's better to work with the Fourier transform, okay? The Fourier transform of the probability of work, the name is characteristic function, okay? If you take the Fourier transform of the distribution, the probability of work that I show you in the first picture, then you obtain this. This is the characteristic function. Is the product of this exponential, when this is the final Hamiltonian, this is my initial Hamiltonian, and these two unitary operators are related with the process, with the movement of my parameter. Okay? So what I say is that I want to work with a quench. Okay? So if I have a quench, this time tend to 0. And this time tend to 0, this is the unity. Okay? And in this case, for a quench, this is the characteristic function is this one. Is the trace of two operators, and this is the initial state that is a thermal state. Okay? But if you see this operator, maybe you are not familiar with this, there is a evolution, okay, that is with H0, and this another evolution with this perturbed Hamiltonian, okay? Maybe you know, this is related with logarithmic echo, okay? This is a quantity that people work in the last 15 years in the community of the coherence, quantum chaos, or whatever. Silva showed this relation that is very simple, that the characteristic function is related with the logarithmic echo. Okay, so in the case that we have a quench, okay? Okay, because this, probably you don't know what is the logarithmic echo, I will make a small introduction. You can see this is a volume that we have in about all of the logarithmic echo with Rodolfo Jalabert. We edited with Horacio Pastatsky, Rodolfo Jalabert, Arseny Gusev, and myself. And there is an Scholarpedia review that it's very new. This is the logarithmic echo. The logarithmic echo is you have an initial state, okay? And you evolve with two Hamiltonians, okay? And the idea is the logarithmic echo, you can think about this quantity. You can see here that the logarithmic echo is the modulus square of the characteristic function when you change u for t divided h bar, okay? So let me show you what is the physics behind the logarithmic echo. The logarithmic echo, you can think this quantity in two ways, in two different ways. Let's take an initial state and evolve both states with two different Hamiltonian. And then you compute the overlap. Of course, what is the measure? This quantity measures the sensitivity to perturbation because you are evolving to the same initial state with two different Hamiltonians. But you can think in the same quantity in another way because you can evolve this state with the Hamiltonian u, and then you can evolve backwards with the perturbed Hamiltonian. And then you make the overlap the same. In this case, this quantity measures the irreversibility. Okay? This quantity, we start to work nearly in 2000, but the important thing is that this quantity has a regime in which the decay of this quantity does not depend on the perturbation, on the relation of these two Hamiltonian, depend on the Lyapunov exponent, of the chaos, of the classical chaos of the system, of one of the system. Okay, and this is when the people saw this result, all the community of quantum chaos, of many people start to work on this. And in fact, for finite. Yeah, yeah. In fact, I don't have time to show you, but we study, they are regime in time, they are regime in perturbation, it's a long history. Okay, this quantity is very important in quantum chaos, in quantum computer, in mesoscopic physics, in decoherence. And there are many experiments. There are many experiments in many different setups. In fact, we are doing experiments in Buenos Aires using sound, okay, that is very cheap, because in Latin America, make experiments, it's very expensive experiment is very difficult. But there are experiments in NMR, elastic wave, microwave billiards, cold atoms, okay? You can see in the Scholarpedia, there is a list of all the experiments. So, okay, so we have a quench. I show you that we have a quench, and when you have a quench, then there is a relation. We can apply all what we know about the Loschmidt echo for the probability of work. Decisive representation. Okay, one of the problems of a semiclassical theory is, in chaotic system, is that the number of orbits, maybe when I talk about semiclassical theory, is you write a quantum object only classical information, of only using classical orbit. Okay, this is a semiclassical theory. If you, the problem is that the number of orbits in chaotic system grow exponential with time. Okay, so it's very difficult to make as a good semiclassical theory for chaotic system. But one of the most important results that people did in the Loschmidt echo community is it's possible to write. This is the name is the fidelity. The modulus of this quantity is the Loschmidt echo. This is again a trace. With this quantity, this was done by Banachek and Heller in 2004, and there are many papers. In fact, in the proceeding that I show, there is a demonstration of this quantity. This is dephasing representation. Look, this is the Wigner function evaluated in the an initial point, and this is the idea. Let me see the idea of the dephasing representation. You move in a classical trajectory, okay, and you compute this quantity. This is the difference between the energy of the perturbed system and unperturbed. By the sum is only an initial state, okay? There is no problem of all the semiclassical theory when you want to go from this point to this point, and you have to find all the classical orbits here. And this is impossible because it's a very difficult problem. Here, you have to sum only in initial state, okay? Well, this is very successful. This is another point of that I will use. And this is an example. This is the Loschmidt echo, the fidelity modulus for a very known chaotic system. This is the cat map. Look, the symbols is the quantum, and the crosses are the semiclassical that I compute. Very simple with this formula, okay? And look at, we can fix the quantum result very nice, but with using only classical information, okay? So, I explained the Quench, the dephasing representation, and the quantum ergodic conjecture is that essentially the wave function, the Wigner function, are the identity, okay? Are equal distributed in whole the energy of the system. So I will mix very simple these three objects, and I obtain this very simple formula that maybe you see. I say, okay, this is complicated, but it's very simple to compute this object. Okay, so we have the semiclassical. This is our main result. This is the semiclassical characteristic function. Okay. Okay, but you see this and say, okay, but you have to show if this works. Okay, first point. If you take this expression and you take the limit h bar, I don't want to show the one page of formulas, but very simple, you can show that the Fourier transform of the semiclassical characteristic function, you tend h bar to 0 and compute the Fourier transform, and you obtain exactly the classical distribution. Okay? So what I show is that this vertex, it's okay. Okay? I show that the semiclassical, if you tend the limit h bar 0, you obtain exactly the classical distribution. Okay? So, but the problem is what happened here. Our semiclassical theory can describe the quantum mechanics. Okay? I can show analytically. In this case, I have to go to an example and show if this works. And this is not simple to compute this in a chaotic system, not simple, the quantum mechanics, but we know how to compute this quantity. So let's see if our semiclassical expression works. So let's take a system. I'm going to take a system that I know how to compute things. I came from the quantum chaos community. We know how to compute the wave function and everything in a billiards. Okay, that billiards are difficult to make the numerics, but we know how to do it. And this is my process. My initial system is a Bunimovic stadium billiard. Okay, this billiard is like a stadium. Okay, and then the Quench, I go to as the same system, but I turn on this potential, okay, for Gaussian, okay? I can do whatever, okay? I put a soft potential inside my billiard, okay? Okay, I have to compute the states, I have to compute the quantum mechanics. That is completely not easy. I don't want to go into the details of this calculation, but let's see if my semiclassical theory works. This is the this is the temperature, 64. The mean level spacing of my billiard is 7. Okay, so for my calculation, I am using my quantum essentially less than 10 states. Okay, so we expect that the semiclassical theory doesn't work for describe something with 7 states. Where the black curve is my semiclassical calculation, and the blue one is the quantum. It works nice. We have this peak, these quantum peaks that we can describe, but in general, it's okay. Okay, let's go. Let's take a bigger temperature. So in fact, we have more energy levels. This is approximately, you have to divide it by 10, is approximately 30 levels. Look, the classical, the quantum and semiclassical were very nice. And you enlarge the temperature, it worked extremely well, my calculation. And it's very easy to compute this quantity semiclassical. I don't have time to show how to compute, but it's very simple. Okay? Okay, let's see. In this picture, I want to see if I take my probability of work semiclassical, and I want to see if this probability of work match with the Harsinski identity. To have the Harsinski identity, you have to fix this line. And look, these points are for, this is the temperature, okay? These points are for very small temperature. But if you engrow the temperature, look, your semiclassical points perfectly match with the identity. So the probability of work that I obtain using a semiclassical theory work perfectly. Okay? So, I say that I can do analytical expansion in H bar, and I can show exactly that in the semiclassical limit, my semiclassical expression works explain the classical limit. Okay, but let's do it in the numerics. Okay, let's change H bar in the calculation in the quantum, and this is the calculation. The quantum is the black. Okay, this is the classical. If H bar is 1, this is the curve. This is a probability. Probability of work, this is work. Okay? And if you see this, if you get small the H bar, okay, the probability of work become the classical one. Okay? So you can see the transition. Here you can see the quantum to classical transition. So our semiclassical theory works really good to describe the quantum and the classical. So I can make a summary of the first part. Is we use the very Boros conjecture and the very simple semiclassical theory to obtain an analytical expression of the characteristic function for the probability of work done on a generic system under a sudden quench. Okay? So we confirm the corresponding principle, thus validating the definition of quantum work as a two-projective measurement process. So what I'm showing is that the two projective measurement processes is a good way to define work in quantum mechanics. Okay? But of course, the question is, okay, but the first point is you have a sudden quench. Okay? But in life, okay, in your experiment, many people show experiment. In an experiment, you move your parameter slowly or rapid, but not sudden quench. Okay? What happened? It is possible to do a theory like I did for a general process when you change your parameter in any way with any velocity. Okay. I want to describe this is my parameter that goes from 0 to t, but now this function can have any value. Okay. This is what I want now. Okay, so as I said, this is the characteristic function. This is my starting point. This is the Fourier transform of the probability of work. Okay, this is the object. It's very simple. It's very simple using the probability of trace and many things. Look at that. I put my evolution operator here. Okay, and look at this. This expression looks like here a Hamiltonian and another Hamiltonian. It's like the case of a quench, but not exactly, because this is not a Hamiltonian, okay? This is not a classical Hamiltonian that I need to apply the dephasing representation, okay? But we make an answer, okay, about the Hamiltonian, okay? We say that the classical Hamiltonian corresponding to this sandwich, the classical version of this object, we say that this, look at this, is the Hamiltonian when we evolve the Q and P inside with the non-perturbed Hamiltonian. Let me show the idea. This is a trajectory of the non-perturbed Hamiltonian, okay? This is my trajectory of the non-perturbed Hamiltonian. Then I take any point of this trajectory and I evolve with this Hamiltonian, with the time-dependent Hamiltonian. This is very simple to do, okay? Each point, and we obtain a new trajectory. This is the new trajectory that I use for the semiclassical calculation. And the calculation is essentially the same, okay? Not essentially the same, but because to do this classically, it's, you know, you have to apply Runge-Kutta, but it's okay. You can do, okay? But, of course, we use this ansatz, okay? We compute because it's not simple. If you have a classical Hamiltonian, you can quantize in some way. But I'm talking another thing. I have an object, and I want to obtain the classical version. And this is completely not easy. If my process is a symplectic operator, this is exact. Okay, this is exact. But it's not general. Okay, so again, this is the same semiclassical with this new definition. Okay, this is essentially the same. Okay, and let's try to see if my ansatz works. Okay, let's try to see if my new semiclassical object can describe. Now, my process is different. Okay, now my process is I have an initial stadium billiard, but now I take 4 of these potential of Gaussians, but this grow with a velocity. Okay, my process is to enlarge my potential. No, like a sudden quench. I enlarge in a time with a velocity. Okay, I enlarge these packets. Okay, and I do the same. Okay, again. The quantum, now I have to compute first the quantum calculation, okay, of the probability of work. And this is really not simple, okay? There are only one paper that people can compute the probability of work in a system that is chaotic and something like this. It's a very difficult computation, okay? And here are our results. This is for, I don't remember, this is for temperature 32. Only five states, 5 quantum states are in this probability of work. And look, okay, the quantum and classical is the same. The black is the semiclassical and the blue is the quantum. Of course, these peaks you can describe, but the decay is more or less you are describing good. This is the characteristic function. Look, you can describe the short times, it's okay. But if you enlarge, look, you can describe pretty well the probability of work. I am describing the probability, the quantum probability of work using only classical information, okay? Again, let's see if my distribution I can use to compute, okay? If can use to compute the Jarzynski identity, but to Adolfo you give more than 10 minutes. Okay, no, I'm finishing. Okay, and it's work again very nice. Okay, and now we are like, you know, like Argentinian. We are okay. We can do more, and we say it is possible to use, because one of the main points is we are using chaos to use this. It is possible to use my semiclassical expression in an integrable system when all my hypotheses are not really good. Okay. This is, I take this system. In this paper, these people compute the work distribution exactly, analytically. I take this system because it's the only system that you have analytical probability of work, okay? And essentially, it's an harmonic oscillator when you change the frequency with time, linearly. This This is the harmonic oscillator, but in this case, the frequency change with time, and linearly, this is the change with linearly with time, okay? Okay. The blue curve is the quantum result. And the green one is my semiclassical calculation. Look, I can describe really nice the decay, the short time decay. Very nice. This is not the probability of work. This is the characteristic function. But there are revivals that I cannot describe. Okay, and we are trying to see how to manage with this. Okay, so the first part you can find in this paper. The second part I sent on Monday when I was here to the archive. And these are my two collaborators, Ignacio García Mata, he's in Mar del Plata in Argentina, and Augusto Roncaglia is also in my university. So thank you very much for your attention.
Thank you for this very pedagogical talk, I must say. So are there any questions?